This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Only 3 people.
Good morning. So today this is a non-examinable lecture. So I have specially written not included for the final examination so that there is no confusion. So the topic is power amplifiers. Then why I am teaching this particular topic is because we don't have much time to teach everything in the amplifier domain. But then power amplifiers are important, and then there are some important concepts that is in the power amplifier. So because you are taking electronic circuit design, I want you to be mastering most of the important concepts. So that is the reason I am teaching you this one, this power amplifiers section. And this is also connected to the amplifier design. So this is not included in the final exam. Yeah, before going to the emitter follower, because we studied emitter follower. So you graduated and then you took electronic circuit design, and then you are working as an electronics design engineer who is designing an amplifier. So when you are designing an amplifier, the amplifier load is different. Means you might be designing an audio amplifier. When you are designing an audio amplifier, what will happen is your load is a coil which needs lots of current. Maybe you are connecting to something else, and then so your design is the following. So you have designed a simple amplifier. It's a common emitter amplifier, and then you have designed it. So this is your V in. Maybe this is I'm going to take a microphone. So you are designing an audio amplifier. Then this is your VCC. Then it's working. It's meeting the specification. But then the problem is you got a speaker. So your speaker, the impedance for the speaker is this is equivalent of maybe 8 ohms. That is the output impedance of the speaker. And then inside the speaker you got lots of coil. And then you got one amplifier, and then this is the block A. So this is amplifier. But then when you want to connect to the speaker, so you are going to connect this amplifier to the speaker. Then you found out your voltage level is okay, but then your current is not sufficient. You know what I meant? Because when you want to drive some coil, you need more current. And then the speaker definitely has so many coils inside. The speaker could be some other load which needs maybe more current. Then if you find out here your voltage is not sufficient, current is not sufficient, then what you can do is if voltage is not sufficient, what you will do? You can put maybe stage 1, then you can connect another stage 2 amplifier, and then you can boost up the voltage. So you can, then for current amplification, what will you use? Based on your knowledge, you want to amplify now current, because for the speaker your current requirement is more. So you need something to boost your current. But when you are boosting the current, what you are doing is you got the voltage, you are boosting the current. Then what is happening is you are boosting the power. So that's the reason power amplifier means that is towards the end of the stage. That is mostly you connect just before the load. That is for boosting the power. Power means the current. Then based on your knowledge, you want to connect to the speaker. So speaker I am going to connect like this, and then this is the ground. And then maybe this is the 8 ohms. But then what you can do here in order to boost the current? Yeah, so you can connect an emitter follower. So that is a simple design. So what you can do is, if you connect to an emitter follower, maybe you can design a current source, or you can connect a very high resistance here. And then, so this will solve some of the problems. I wouldn't say all of the problems. If you do this one, what is happening is, this is your voltage. The voltage for the signal, it will pass through. And then the current is IB here, and then your emitter current, IE. So emitter current for the signal will be maybe beta times IB. So if this is equal to 2 milliamps, and then if your beta equal to 100, then you are getting how much? 200 milliamps emitter current. So then, and the voltage, emitter follower will make sure that this voltage is Vs, and then this is approximately equal to Vs, slightly less than Vs. You know what I meant? And then you got the same voltage, but then you have amplified the current so that you increase the power. So this is a power amplifier. But then a simple power amplifier is this one. But then the problem. So when you are connecting a current source here, you will be biasing this current source maybe for maybe this case I am just going up 10 milliamps. Maybe you bias this current source for 10 milliamps, and then 10 milliamps emitter current will be flowing. That is a DC. For the signal current, what will happen is that will pass, that will come here. So here your 10 milliamps, that is a DC current. Due to signal you are getting how much? 200 milliamps. So the 10 milliamps plus 200 milliamps will come here. 10 milliamps will go through this current source, because current source will not take more than 10 milliamps. It will not take less than 10 milliamps. Always 10 milliamps will flow, and 200 milliamps will go through this to the load. So you are fine. But then this is a problem. So when you have a common collector stage or emitter follower, then this is your speaker. Maybe that is 8 ohms. That's a speaker. And then this you may have biased for the 10 milliamps. This is a VCC. Then here you are going to connect a signal. So my question is VB. So usually VB, which is equal to around 0.7 to 0.8 volt. Here we are going to take 0.8 volt. Then when it is increasing, so it is going to increase the signal, and then it is maybe 0.8, and then what happens is you are getting an output here. But then what is happening is, when due to some case, if this signal here is much less than 0.8 volt, you know what I meant? If this is less than 0.8 volt, maybe the variation is something like this, but then suppose this point is less than 0.8 volt, or this region is suppose falling slightly less than 0.8 volt, then what will happen to this transistor? Off. When it is off, what will happen to this current source? Current source, because current source you have biased it to 10 milliamps. If you connected a load, current source will look for somewhere whether it can draw the current. Then what will happen is, this transistor will be off, then the current will come from here. Okay, so then this voltage will become kind of a little bit negative, but then what is happening is, then you are kind of getting a DC kind of current, negative, not your signal. So that's a problem when you are using this one. So this current source will draw current from here, so that you will see a small negative voltage here, because you are drawing current direction is from ground to here. So then when you are designing so this is kind of a, I wouldn't say that a proper power amplifier. Maybe you can say yes, emitter follower is a power amplifier, but then this one got an issue, a current amplifier. This issue is a problem. Then what we can do? So that's the beginning. So here I have mentioned that one. So here this is your signal. So this is your DC voltage, that is a 0.76 to 0.8 volt. So usually what will happen is you will make sure that here you have got how much voltage, your bias voltage is 0.8, because your signal will be riding on the top of 0.7 volt. This transistor first will bias it. But then you got a sinusoidal signal that will be riding on the 0.8 volt. You know what I meant? Because you have to bias your transistor first, and then your signal will be riding on the bias signal. But what will happen is, at some point when the signal is coming negative, this point what is happening is maybe after this point your signal is negative, means then this transistor will be off. When this transistor is off, what will happen is then the current source will take current from this RL to the ground. So here we have connected plus 5, here we have connected minus 5, and this current source we biased for just 32.5 milliamps, just an example, and then your speaker got 8 ohm impedance. Then I1, what is the current of I1? This I1 equal to IC, because our assumption is IC approximately equal to IE. So plus V out by RL, because that is the current it is flowing here, this I1. Then what is happening is this is your input signal. So input signal is the dotted line, and then input signal is pale blue, see light blue. So your input signal is riding on the top of 0.8 volt. So how do you get to 0.8 volt? Because here you have got resistor bias, and then you biased this transistor so that it is in the active region. Then you are connecting a sinusoidal signal. So your sinusoidal signal is riding on the 0.8 volt. It will increase, and then with respect to that one it will be decreasing, increasing. Then what will happen is when it is increasing, your output also will increase. Why? Because your output here it is already bias is there, and then it will be output also will increase. But then output will increase, and then what will happen is the V in is decreasing. So V in is decreasing, but then when it is decreasing, when it is crossing this point, see when it is crossing this DC 0.8 volt means this transistor will be off, because you don't have the bias anymore. Then see, it current source will draw some current. Depending upon this RL value, you get a negative flat region. You get some voltage, but that is negative, because from here it is drawing the current. The current is coming from the ground to this point, and then the current source will take the current. So you get a flat here. Again, in the positive cycle it is flat. But then you can see here you got some difference, because why it is difference? Because we have drawn like this. Because this is 0.8, this is starting from 0 volt, because here you got a plus 5 volt, here you got a minus 5 volt. So then here you can by adjust how much voltage that is coming. So that is the reason starting from the 0. And then so your output, what is happening is this region, the Q1 is off, and then you are not getting any characteristics of the signal. Actually you are losing this negative signal. So what you can do to solve this problem? So you designed this one, what will happen? Then people will ask, you are the electronics engineer. One way, somebody can straightforward, how about shifting this 0.8 to maybe a bigger value, 1 volt? Is it a good solution? So that this negative is not touching, you know what I meant? So that your negative part is well below 0.8. Is it possible? You know what I meant? So at the moment what is happening is here you got a 0.8 volt. Okay. Here you got 0.8 volt. And then what is happening is your signal 0.8, and then this is your input signal, input. Then input signal is like this. Okay. So during this period your transistor is on, because your voltage is above 0.8 volt. But during this period is a problem, your transistor is off, because your VB is going below 0.8. No, but then your negative signal, this signal, your signal is riding on the top. And then one way is you can push this one further up. But then VB, if you try to increase, your current will increase and you burn the transistor, because your IC equal to IS exponential VB by VT. So VB, you can't make it 0.9. You can't make it because then what is happening is you might burn your transistor. Then in order to avoid that one, what people came up is oh, it's not moving. Yep. So they came up with 2 transistors. So that is called a push-pull stage. So that's the reason you might hear push-pull stage or class B stage. And then this one, people often say maybe class A stage. So this is called a class A stage. So you might hear some people often talking about, oh, this is a class A amplifier. Means this is a... Sorry? No, that this value is depending upon, because this current equal to IC plus V out by RL. So this voltage is V out by RL is decided by the value of RL. So this is just some value I put in here, and then you may be getting a bit negative value. This value may be different depending upon the value of RL. And so here what you have to understand is depending upon the value of RL, this voltage will be slightly different. But then you get a negative, so that is the main point I am showing here. You get a negative voltage because current is coming from the ground. So the value will be different depending upon the RL value. Again, how much current you are setting in the current source, depending upon that one. So that is called a class A amplifier. In the class A, you get only half amplified. You know what I meant? A half cycle amplified, like a half wave rectifier. Then people came up with the idea push-pull amplifier. So that is called a class B. So push-pull. So you can understand this. So here is an interesting way it is operating. So V in, that we connected to Q1, and then same V in connected to the Q2. So that pretty much like your mid-semester test last question. Little bit different. This is NPN. This is NPN. Okay, so then somebody maybe thought, that last question we made up deliberately to complicate you guys. No, that is kind of, there is a circuit, something similar. So that is called a push-pull stage. And then VB, when you connect to this V in, what is VB? VB minus VE. What is here? This is a PNP, so we will be talking VEB. So that is equal to V emitter minus V base. Here what is happening? If you connect one more, instead of the current source, now you got one more transistor, and then you are connecting input to the base of both the transistors. In this case, what happens is when your signal is rising, when your signal is increasing, what will happen? Because this will become 0.8 volt, and then this transistor will be off, because this is a PNP. In order to be PNP on, here it should be either ground or negative, and then here it should be more voltage, because VEB, VE minus VB, that is should be higher value. So V emitter, so emitter is this one, base is this one. So base should have less voltage than the emitter, then only this PNP will be on. So during the rising edge, what is happening is this transistor, what is the voltage? Yeah, so during the rising edge, so here you have got to say 0.8 volt. Then what is your VB? If you assume that V out equal to 0 first, so then what is your VB? VB, that is equal to 0.8 volt minus VE equal to 0. So 0.8 volt. What is VEB? Because here it is, our assumption is 0, and then minus VB, that is equal to 0.8 volt minus 0.8 volt, so that this transistor is off. So during the positive cycle, this transistor will be on. Then what is happening is, see, you are getting the signal amplified. During the negative cycle, this voltage becomes, see, say minus 0.8 volt, and then your VB minus 0.8 minus 0, then it will become negative. But during negative cycle, this transistor will be on, and then this RL, the current will come from the ground, and then this transistor will, emitter current will come, and then collector will go through this point. You know what I meant? And then so this transistor will be on, so that your signal is, when you check it, then what is happening is you will get actually amplification like this, but then you are having some problem, some region you are still missing. See, that is Q1 and Q2 of some region. So here, why that Q1 and Q2, here you are not getting the amplification? Because here I have taken 0.8 volt, here I have taken again minus 0.8 volt. If you connect like this, your signal without any DC bias, what will happen? Without DC bias, if you connect like this, below 0.8 volt, both the transistors will be off. You know what I meant? Here, if you are not providing any DC bias, so that is called a dead zone. See, that's the reason this region it will not work, because your signal is increasing. See, your signal is increasing, but then nothing will happen in the output until your signal is above 0.8 volt, that is your VB. Then your output is, see, output starts. But then your signal is starting from here actually in the input until it reaches 0.8 volt, that is a VBE, required for making this transistor on and giving the forward bias. Then it is fine. Again, when the signal is falling below 0.8 volt, you don't get anything, but in the negative side you get amplification. But then still you got a dead zone here. Then the dead zone, how can you avoid a dead zone? Because both the transistors are off for the voltage below 0.8 volt, this region. So how can you avoid this dead zone? By providing a bias. But then how to provide a bias when you have this type configuration? That is a question. What? So self-bias. So somebody said self-bias. So you are putting like here this one negative, and then you are connecting here. But then self-bias is a slight issue because then your current will be very high because you are connecting your collector directly to the base. Maybe you can connect a resistor here. One option. But then there is a problem. That problem is that when you connect, yes, that's a good way of thinking. But then when you give a bias, you are not only giving this transistor, you are also giving to this one. Because you got, both are connected together. Because that's a little bit complication. Then people came up with the idea, if you give a bias here, simple idea, then you can avoid that problem. But then you can't connect a cell inside the chip or anywhere. Then if you want to get the effect of a cell or a voltage, suppose inside somewhere or even in your discrete circuit, you want to connect some DC voltage, the best way to do is connect two diodes, because diode drop is 0.7 volt. But obviously you have to connect to the voltage. And then you can, if you connect this VB here, you don't have that dead zone problem. And then you can connect maybe two diodes, and one for this one and one for this one, biasing. But then when you connect this diode, then this diode should be getting some power from somewhere. So that is the reason then what will you do? You have to connect this to the VCC. Then we will not short it directly, we will use a current source, because then this current source will set the current, and then this current will be sufficient for biasing this Q1 and then sufficiently for flowing through these diodes and giving the bias. You know how it is evolving. And then since VB voltage, that is equal to VB1, VB2, a natural choice will be two diodes in series. And I1 in the figure B, here I1, this one, is used to bias the diodes and Q1. So you can set this current, and then you can use this diodes, you can bias it, and also you can bias the Q1. So then if you do this one, then what will happen is you don't have that dead zone problem. So now you don't have this issue. You will not lose anything here because this much is covered. Here the problem is you are directly connecting signal here. When you directly connect your signal to the input of the amplifier, what is happening is your VB, you know what I meant? This issue happened. Why? Because you got this amplifier, then what is happening is without any bias. So you are not connecting any bias. Without any bias, you are connecting some signal here. Then what will happen is your output, what is happening is you will not get anything until 0.7 volt. When it is crossing 0.7 volt, you get signal. When it is falling below 0.7 volt, you don't get any signal, because you are directly connecting signal to the base of the amplifier. Then if you don't have the bias, then above VB only you get the output. So that's the reason we got a class A, class B, then class AB amplifiers. See, so firstly we got a class A, so that is this class A. This is the class A amplifier. Then we came up with the idea, connect one more transistor, so that when during positive cycle Q1 will be on, during the negative cycle Q2 will be on, and then Q2 will be getting current from the ground through RL, and then that is providing the emitter and collector current. But then class B is good, but still got a dead zone. Why? Because you are connecting your signal without any bias to the input of the Q1 and Q2, so that you don't get any signal below VB. So that is the reason you are getting a dead zone. Then you came up with the idea, if you provide a bias to both the transistors, you don't have that issue. In order to provide a bias, we connect two diodes, one diode for Q1, another diode for Q2. But when you connect a diode, the forward drop is 0.7 volt. So that will solve the problem, 0.7 to 0.8 volt. And then when you connect a diode, you have to power the diode. Then we have to connect this diode, not a good idea directly connecting to VCC, because that's a VCC is maybe 5 volt. So that's the reason we connect a current source, and then this current source will be biased appropriately. It's enough for this D1, D2, and then for the bias in this Q1. So this is class, you can say that AB. So class A, class B, class AB. See, you can see that class A, then class B got this issue, dead zone issue here you can see. Class AB, you don't have that issue. And then class A got efficiency 25%, class B got efficiency 78.5, class AB got less than 78.5 actually. Then when you are having this stage, this is called a push-pull stage. Why it is called a push-pull stage? Because as I said, during the positive cycle, you are pushing the current through RL. You know what I meant? See, push-pull. During the positive cycle, you are pushing the current through RL. Q1 is providing the emitter current, then this current is coming and pushing through this RL. Then during the negative cycle, you are pulling the current from the ground through RL. See, you are pulling out the current. So that's the reason it's called a push-pull stage. So then now you know why it is called a push-pull stage. Then in the market you will see push-pull amplifiers. You can buy push-pull amplifier. Then you should not think that push-pull is somebody's name, not his name, because it's pushing the current, pulling the current. That's the reason the name push-pull amplifier. And then this is an example. This current source maybe you set for 10 milliamps. Then 1 milliamps maybe for biasing Q1. Remaining 9 milliamps will flow through D1 and D2. And then this current is coming here, some current will go through RL, and then see also some will go here, it will come here, and then V in is, your signal is here, you are connecting. Maybe this is the output of another amplifier, and then you will be connecting here because this is the output stage. So I in, you can write down I in, which is equal to I1, this I1 is coming, minus IB1, because I1 minus IB1 is coming down, plus modulus of IB2. Why? Because this current is joining here. So that's the reason this is expression. Then how this is working? When the Vin is positive, your signal is rising, then what will happen? When you have more positive here, what will happen to IB1? When you have more positive here, means you, when you connect a diode here, this is a PN, and then this should be negative. But if you connect a positive here, what will happen? If you have positive voltage here, Q2 will be directly off because this is a PNP transistor. And then when you have positive here, what will happen to the current flowing through the diode? Will increase or decrease? So the question is, so you got a diode, then you connect a positive voltage here, and then maybe you connect a resistor and then RL. So this is the diode. Then my question is, this is ground now, and then here you have connected 5 volt, then some current is flowing, I. Now I am not grounding. Here I am going to make some positive, maybe 2 volt. Whether this current will increase or decrease? Yeah, the same thing will happen here. See, here this diode, what is happening? When you have a positive voltage here, then this current will decrease because the diode current will decrease, I1 minus IB1 will decrease. And when you have a positive here, then what will happen? This current will increase. Because when this current decreases, whatever the current coming through the current source will try to go through this one as well, the remaining current, you know. Because current source, if you bias for 10 milliamps will come here. When you have positive charge, positive voltage here, this coming down, this current will decrease. Then what will happen to the current, that one? So the remaining current has to go through this one. So that Q1 is on, Q2 is off, and IB1 increases because of that reason. So that Q1 is on. If Vin is negative, if this voltage is negative cycle of the signal, Q2 will be on. You know what I meant? Because of PNP, this is a PNP transistor, so this need a negative. So this will be on, But then when this is negative, what will happen to the current through this D1 and D2? It will increase. When that is increasing, you don't get a sufficient current for Q1 base current. So that Q2 is on, Q1 is off. And then if Vin equal to 0, when this is equal to 0, you are grounding, means you don't have any signal. Still, because of this current source, D1 and D2 will provide a bias for Q1 and Q2, so both are on. So this is called push-pull amplifier, but then this will come in the category of AB because you don't have any issue of the dead zone. So that is the reason in the lab, then again we can make it sophisticated, because here when you see, you are connecting your signal here, but more elegant way of doing is maybe this connection can connect to the center of the diode. Why? Because this diode is used for biasing Q1, this diode is used for biasing Q2, so that we can shift actually this point here. That is the reason in the lab we have got such an amplifier. So how many of you thought about this amplifier? Because you have used a microphone, then you have got a speaker. You got a speaker, that is the reason we got a push-pull stage here, output stage. Because we want to amplify the current. When you amplify the current, we don't want to have dead zone, we don't have any issue. That's the reason we will be using this configuration. So this configuration is slightly modified than this one. See, here you got a current source for Q1. And then what we can do is the same arrangement we can do for Q2 in order to make it symmetric, and that is much better design. And then you can connect your signal here actually. Then this diode you can use for biasing Q1, this diode for Q2. So that is the reason this design came. So you got two transistors, same push-pull. Now you got a current source here, now you got a current source here. And then you got this diode is for biasing this Q1, because when it is on, you get around 0.7 or 0.8 volt depending upon the diode drop. That used for biasing Q1, and then this diode is for biasing Q2 when you don't have any signal here. And when it is 10 milliamps, it is coming 10 milliamps, and then it will branch out, and then it will come through, and then it will branch out, it will come here, and then if this is 10 milliamps, and then here the 10 milliamps current will come here. So that is the reason instead of current source in your design we have put resistances, see, RB3 and RB4. Resistance also will work. And how this will work? When you have a signal here, when you have a positive signal here, your signal is rising. Then we will take maybe this as an example. So when the signal is rising here, then what will happen to the current through the diode? When the signal is positive here, what will happen? When the signal is positive, what will happen? Current through the diode will decrease. When the current through the diode decreases, more current will go through Q3, so Q3 will be on. When this is positive, more positive, then what will happen? So this will be off. And then, so this will be pushing the current through RL. During the negative cycle, what will happen is more current will come through this diode so that you don't get enough current for Q3, and then this will be on. And then this will be providing the current for this RL. Same as push-pull geometry. So here I have written VD1 which is equal to VB, because VD1 that is equal to VB which is equal to V out, and then which is equal to V in. Yeah, so this is important. ID1, your ID1 equal to I1 minus IB1. ID1, this ID1 that is equal to I1 minus IB1. ID2 plus IB2 equal to I2. And then ID2 equal to I2 minus IB2. And then if I1 equal to I2, we can make IB1 equal to IB2. So that is the reason. So this is a standard output stage. And then during the positive cycle, this will be off, so that this Q1 will be providing current for the load. During the negative cycle, Q1 will be off, Q2 will be on, and then the current will come from the ground through RL and then come like this. When there is no signal here, still you got a current passing through D1 and D2. D1 will provide a bias for Q1, D2 will provide a bias for Q2, so that you don't have any dead zone. So that's the reason we have used the output stage here, and then we connected your speaker here. And then this is a common emitter amplifier. So this is called a push-pull stage. So push-pull stage is used in the output stage to push up your current. or enhance the power, especially when you need lots of current out the output. That's the reason in the operation amplifier they have got an output stage. That output stage is to increase the current, or a little bit, you amplify the voltage in the multiple stages. Then in the last stage they increase the current, they amplify the current. So that's called output stage. And in the operation amplifier, in all the amplifiers, the output stage is the last stage. Now my question is, somebody will ask you, you got this amplifier, that is a common emitter amplifier. Then what is this stage? Because you have done the lab. What is the use of this stage? What this stage will do? Do you think it's a buffer? Yeah, otherwise I will go and reduce your mark for the lab. So this is an amplifier or something else. Will this circuit do amplification or not? Second stage. Yes. Okay. No. I'll reduce your marks. No. So today you both got some work. You have to breadboard the circuit and then test it. See the signal here and then see the signal here. Will you get any amplification? Because this is a PNP amplifier, because this is a multi-stage amplifier. See, the lab name is multi-stage amplifiers. So this is an amplifier, this is an amplifier, this is obviously a current amplifier. So definitely this is an amplifier, but then this will also do some level shifting. So amplifier plus level shifting. So that is the reason. Then my question is, people will ask, this is, maybe you did the lab. Maybe tomorrow somebody, maybe your friend will ask, yes, this is a multi-stage amplifier. Why do you need 3 stages? You will say that, oh, here we are doing the voltage amplification. In the last stage, we have to amplify the current so that we got the output stage. It is a push-pull stage. You can explain the working principle. This is an intermediate amplification stage, further amplify the voltage. Then at the end, we are amplifying the current. Then your friend will ask you, why do you need a PNP here? Why can't we use another NPN amplifier? Why can't we use another NPN? Then you can't say that, the lecturer put this circuit diagram in the lab manual, we can't change it. Yeah, this is a genuine question. Why can't we put NPN amplifier there? Why do you need a PNP amplifier? Well, so my question is, if you connect a NPN amplifier, whether the circuit will work or not? The circuit will work, how many of you think? If you connect NPN amplifier there, the circuit will work or not? Instead of PNP, I am going to connect NPN. Will this circuit will do amplification? It will do amplification, how many? It will not do amplification. Nobody. So what is the in between then? No, definitely it will amplify the signal. Even if you put NPN or PNP, this will definitely work it. It will do the amplification because it's a multi-stage amplifier. But then we have deliberately made this PNP because there is a reason. Why? Because I will go to this one. So if it is because your amplifier is a DC coupled multi-stage. So what do you mean by DC coupled? DC coupled means your output is directly connected to the base of another amplifier without a capacitor. So that is called DC coupled. If you use a capacitor here, that is called AC coupled. If you directly connect it here, means if you put a capacitor here, advantage is your DC, this DC voltage is isolated from this DC voltage. So only the signal will pass through. Then if you connect a DC coupled means you are directly connecting. Then directly if you are connecting, there is a problem. If this is equal to 1.3 volt, if this is 1.3 volt, here you are getting around 1.3 volt. Then in order to make this transistor in the active region, your collector voltage always should be greater than 1.3 volt. Okay, then you have to keep this maybe not 1.3, maybe around 2 volt. And then your DC coupling here, this one. And then here now you got 2 volt, and then here this should be more than 2 volt. You know what I meant? then your output voltage is level is shifting up. You know what I meant? Your requirement is increasing. So here it is now, this output is 1.3, then here you need around more than definitely 1.3 in order to make this transistor in the active region. Then another stage is here, then this voltage should be greater than this one. So if you go to 3-4 stages, what will happen is then you don't have any space for amplification because your 10 volt will come. Yeah. So in order to avoid that one, what we do is we will put a NPP level shifter, or we can put a level shifter, so that level shifter will reduce the requirement, or you can use a PNP amplifier that will solve the issue. So in DC coupled multi-stage cascade, the output bias level of each stage increases to maintain the collector more positive than the base. If this voltage stacking is severe, little swing room is left in the final stages of the cascade. Means then when you have 3-4 stages, then this voltage will become maybe 8 volt, but then your supply is 10 volt. Then it will affect your voltage swing. Then people will ask you, why do you need a DC coupling in the amplifier? Because if you connect a capacitor here in between, then you don't have this issue. Yeah, but then I am happy to bias it. Then why do you need a DC coupled amplifier? Even if you check inside the operation amplifier, you don't have the capacitor, only one capacitor. It is not AC coupled, it's all DC coupled. So why do you need a DC coupling? So if you don't have DC coupling, you can't amplify DC voltage. As simple as this. You know what I meant? Because DC coupling means, that's the reason we are using DC coupling. Means you got an amplifier, and then it is coming, then another transistor is coming, then the direct coupling is called DC coupling. If you put a DC coupling, this is the problem. So if it is 1.2 volt, here you got 1.2 volt, this should be more than 1.2 volt in order to make this in the active region, maybe 2 volt. So, but then in order to avoid this one, we can put AC coupling, you can put a capacitor here, then you provide a bias for this one separately. Then your DC, this voltage is isolated from this voltage. But then the problem is, when you want to amplify some DC voltage, this capacitor will not pass the DC. So this is called AC coupling. So we will not use AC coupling if you are amplifying DC voltages. So that's the reason in the operation amplifier, you are using DC coupling inside. I will show you the circuit diagram again, which you are already familiar. So in order to avoid this issue, this cascading issue, the requirement of higher DC voltage, then people came up with, why don't you put a PNP transistor here, amplifier. So if you put a PNP amplifier, actually you can have less voltage here, because this is the base, this is a PNP. In order to make a PNP on, it's not VBE, which is VEB. And then your base can have lesser voltage than your emitter. And then, so that is the reason we are using PNP. When you are using PNP, this voltage can be very small, 0.4 volt, or depending upon how much resistance you connect it. By using a complementary device, that is a PNP, active level shifting can be combined with amplification. So if you are using this one, what will happen is maybe in between you need a level shifter that will shift this voltage further down, kind of a level shifter. But then here the advantage is this is a PNP amplifier which will do the level shifting for you. So now here it is 6.3 volt, but then here it is only 0.4 volt when you take output from here. So you don't have much problem that you are not losing the voltage swing. So that's the reason we got this stage like this. See, now you understood the importance of this stage, why we have designed this stage like this. So here we got, this is an amplifier plus a voltage level shifter. The requirement is, otherwise what will happen is, you have this issue. When this voltage is 1.3, then you need more voltage here, because you want more voltage here, then only this transistor will be on. When you have a couple of stages, then this voltage requirement of base voltage, this will become close to 10 voltage, then you don't get much voltage swing. In order to avoid that one, you can approach two ways. You can connect a level shifter maybe in between. You can shift the voltage, or you can use a PNP amplifier with a voltage level shifter. So PNP you can use. Then you get a voltage level shifting. You don't have that effect. Then in practical power amplifier, some people, this is a block level diagram. If you check a power amplifier, you have voltage amplification. Again you got voltage amplification, then you will see some driver stage, then you got a power stage, then you got a speaker. So kind of like this. Maybe this too like a multi-stage voltage amplification, then you got a power amplifier. Then sometimes in some circuit you will see a transformer instead of resistor here. Then you will be connecting your, here you will be connecting your speaker. See, here you will be connecting your speaker. So this is called transformer coupled power amplifier, transformer. So instead of RC, so you should not be surprised when you see this one. As I said, this is not asked in the exam. This is all for your information. So when you see a transformer, you should not say that, is something wrong with the circuit. No, in the power amplifier, people use these type circuit. So then why do you need a transformer? The advantage of transformer is when you have transformer coupling, you can match the impedance of the speaker with this impedance of your RC. Then also when you have transformer will pass the DC or AC? AC, only AC. So you get AC coupling. So that is so sometimes people use a transformer coupled, again this is in the power amplifier domain. Then the power amplifier, what you have to understand is this is called a push-pull stage, and then you got a level shifter, and then you got this amplifier. Then now we know that the evolution of your amplifier, like this, we came up to here, this type design, and then that's what we used in the lab. Instead of current source, we have connected resistor in the lab, and then we used this PNP amplifier here instead of NPN because we want to get amplification plus level shifting. So if you don't get level shifting, we have this issue. Now we will go to our previous lecture. In the previous lecture, we already said we will be taking V out minus V in. Sorry, V out B minus V out A, because difference between this voltage, then that is two lines, then we can't connect to another stage. Then we came up with the idea we can have only one output. So you can have two input, you can get only one output using this current mirror load, and then you can convert this differential input into one line with all the effect which we already studied. Then, which we already proved it in the previous lecture, when you take only one line from here, that is equivalent of V out A minus V out B, which we already studied it. And then when you have such a one line, somebody asks you to design a simple operation amplifier. So this is a simple operation amplifier. Means what? This one is a simple operation amplifier. So in this operation amplifier, you got V inverting input, non-inverting input, and then that you can design. See, here the signal is increasing. Here the signal you are, see, this is falling down, and then but the output is increasing. Then this one you can take it as non-inverting, because when you connect a positive signal here, you get here positive signal. When you connect a negative signal, you are getting positive signal here. So in the op-amp, when you make it, you will say this is non-inverting, this is inverting. So you got two inputs. Then this is output. So you already designed an operation amplifier by designing the differential amplifier. So if you want to design a bit more sophisticated, what I would say is you take your differential amplifier, then connect to maybe another PNP amplifier. Why PNP amplifier is then you are getting some kind of voltage level shifting if you required. Or you can connect an NPN amplifier. Then you connect your output to your output stage. So when you do this one, you already designed an operation amplifier. You know what I meant? So this is I would say that a basic operation amplifier. So that's how we design operation amplifier. Simple. So now we can increase the complexity. Now you know how to design operation amplifier. Here you got this non-inverting, inverting, and then you got the output. Then you can connect to another amplification stage. Then output should be a push-pull stage to increase the current. So then you already designed an operation amplifier. This is easy because you breadboard a much complex circuit than this one. That is a OTA, operational transconductance amplifier, where you don't have, you will be doing all these things, but you don't have the output stage. This is another example of an operation amplifier. Somebody designed using a chip. It's also in a pretty similar, but then this one you can see the output stage is not sophisticated as we discussed. You know what I meant? This is the less sophisticated output stage. Somebody designed again like this, and then so this is a differential amplifier, and then they have got a push-pull stage here. So different ways you can design, but then these are the chip level designs, but then for you this is the relevant. If you want to design an operation amplifier from discrete components, now you have the confidence. You got the output stage, differential amplifier, you got the output stage now, you know why we need output stage, then this is a differential amplifier, you got one input, you can have a PNP amplifier. I would say NPN also is good, but PNP will do a little